Hey there, this is Arnav from Pebble, and welcome back to the Introduction to Linear Algebra series. In the last video, we discussed a little bit about how we can define a linear transformation to take the vectors in one vector space and map them, much like a function, to the vectors in another vector space. And in this case, this would be the linear transformation T that maps V to W, and we can define T in various ways as per various rules that we discussed in the previous video. And so this is really confusing because, well, now we're kind of studying linear transformations on finite dimensional vector spaces. And that's a lot of words, that's a lot of terms, and it's not really, it doesn't really align with the general thought process of linear algebra, which is to create efficient ways of study and solution. So in this video, I want to talk about matrix representations for vectors and linear transformations and how we can use that efficiently. And so one thing you might recall from a previous video in the last chapter, I believe, is that, well, we can express a vector as a linear combination of a given set of basis vectors, right? And there's only one way to do this, obviously. So we could have a vector v, and if we want to, and we have a basis, v equals v1 through vn, and we want to represent v in that format, well, then there exists some constant c1 v1 plus c2 v2 plus all the way up to cn vn. And so this is the only linear combination of these basis vectors that will work. And so what we can do is, well, this basis, it might not be the standard basis. So we need a way to notate that this vector, this representation of this vector, isn't in the standard basis. And so, well, v, we're going to use this notation of a double-sided arrow, v, well, that's going to be c1, so c1 corresponding to the first vector in the basis, c2, and then we're just going to keep going all the way to cn. So this is showing how much of each vector in the basis we need. And so this, and then we're going to denote it at the bottom by saying that our basis is going to be b. So this is notation to say that this is v represented in terms of perhaps not a standard basis, and how much of each vector inside that basis that we need. Okay, so we call this a coordinate representation for whatever sum it is. And so the subscript here, this just denotes the basis, and this coordinate representation is basis dependent. Okay, so we're not using a standard basis here. And so let's talk about an example here where we can find the coordinate representation for a vector, which is v equals 4t squared plus 3t plus 2, and this belongs to P2, so the set of quadratics, with respect to a non-standard basis, which is going to be t squared plus t, and then our second vector is going to be t plus 1, and then our third vector is going to be t minus 1. So this is definitely not standard, because the standard basis would be, we've discussed this in the past. And so we have to write v as a linear combination of these vectors. So what that's going to turn out to be is we need some constant c1, which, not to get confused with our basis c, which is going to need to have some combination of t squared plus t squared plus t. Yeah, t squared plus t, and then plus c2, which is going to be some amount of our second vector, and then the third one, which is just going to be some amount of our third vector. And so that's going to come out to be c1 t squared plus c1 plus c2 plus c3 t plus c2 minus c3, basically. And so we can generate a system of equations from this just by equating the like powers and doing all of that. So you see 4t here would equal whatever c1t squared, and then 3t would equal all this, and then 2 would equal this. And so by doing that, we get c1 equals 4, c1 plus c2 plus c3 equals 3, and then c2 minus c3 equals 2. And so our solution is going to be c1 equals 4, c2 equals 1/2, and then c3 equals minus 3/2. And so what this tells us is that, well, these are the amount of each vector inside our basis. And so we can use this sort of like a coordinate representation. We're representing it in terms of we need this much of our x's, this much of our y's, this much of our z's, if this was a graphic of just three-dimensional space. And so we're just saying that's how much of each. So the way we're going to denote this using our same system is that 4t squared plus 3t plus 2, this double-sided arrow is going to be 4 1/2 minus 3/2 with respect to what? Well, that's going to be with respect to C, our basis C here. Okay, so hopefully that makes sense how we're using coordinate representations here to re-represent our vector space, or to re-represent some vector inside our vector space with respect to a non-standard basis. So we would basically just create a coordinate representation. And so we can use this to sort of determine linear transformations for a vector given two inputs and some outputs, or some number of inputs, some number of outputs. Okay, so if you know that T is a linear transformation and V is a vector that's expressed, V is any vector in our vector space, well then you know that T of V, where T is a linear transformation, T of V is going to equal T C1 V1 plus C2 V2 all the way up to Cn Vn, where these V1, V2, Vn are our standard basis vectors. And so since we know that from the previous video, well, we can rewrite this just to be C1 T V1 plus C2 T V2 plus all the way to Cn T Vn. And since we can rewrite it like this, well, now it's described completely by its actions on our basis, right? So we know how we can figure out how T transforms the basis, so we can use that to determine how T is going to affect our vector V. And to illustrate that, let's say that we have a linear transformation of R2 into R2. I can't draw arrows today. Can't write either. R3. So let's say that we know that T of, let's say, the standard basis for R2, that's going to give us 1, 2, 0 if we input that into our transformation. And then if we also input the other vector in the standard basis for R2, we're going to get 0, 3, 4. So given these two pieces of information, we can determine the transformation, how it's going to affect any vector inside R2. Okay, just by the basis. Just by the basis. Okay? And so, if we have here that we need to determine TV for any vector, so TV for some vector v that belongs to R2, set of R. Well, if V belongs to R2, then V equals AB, obviously transposed to make it a row vector, for some choice of real numbers A and B, right? So the set of this 1, 0 are bases transposed, and then also the second one 0, 1 transposed. Well, this is a standard basis, right? And with respect to a basis, so with respect to our standard basis, we know that AB, well, that's going to be some combination of our first vector and our second vector based on the logic that we did previously when making it in with respect to a basis. So this. And so if we input AB, just follow along here. It'll all make sense at the end. If we input AB into our T, well then, AB, we can rewrite this, right? So that's going to give us, well, A, T, 1, O, if we're substituting whatever we got here into it. AB, 1, O, and then B, T, 0, 1, right? So we know that, well, this has to equal A. So we're applying the transformation now, right? Because what we understood is that, well, T is just going to be T for any vector V is going to be some operation on the basis times a scalar that makes our vector And so that's going to give us that, well, 1, 2, 0. And then that's going to give us that B is 0, 3, 4. 0, 3, 4. And so A, writing this out, multiplying our vectors and adding them, we're going to get A, 2A, 3B, 4B. Okay? And so now we've basically understood that now we've understood that, well, for any vector AB, this is the transformation that's going to occur for that vector. This is what's going to happen to that vector. That's our linear transformation. And we discovered this by not knowing our actual transformation. We weren't given that. But we understood that, well, any vector is going to be a combination of our bases. And so by using that logic, we can understand that if we're given the transformation for our bases, then we can apply that to understand just exactly how we're going to what the transformation is going to be for any vector. Okay, and this becomes really, really simple at that point. Okay? So, let's do a let's now move on to finding a matrix representation with respect to a standard basis for different standard bases for linear transformations. Okay? Well, actually, before we do that, I want to talk about a little bit of knowledge that you need to have. So if we're taking an n-dimensional vector space and we are transforming it into an m-dimensional vector space, and we have different bases for both, well then we need to be able to describe this as some transformation of our vectors, right? Of our bases. So the way that we can do that is that we can define our transformation of our basis in the n-dimensional. So if we're mapping n dimension to m dimension, well then we can define that, say, in the n dimension we're gonna have v1 through vn, right? So in the n dimension, if we have v1 through vn, and then in the m dimension, whatever that vector space is, we have w1 through wm. And so if we have that, right, well then we can say that the operation, so if we do a linear transformation on this basis, well then we're going to get some combination of the bases from this one. So we're going to get, say, a11 equals, this is not 11, this is 1, so it's coordinate as if it's two-dimensional, and then a21, and then w2, and then all the way to am1, wm. And then we can also get that if this is if we only have two dimensions in n, so only two bases, well then this would be 1, a2, so this would be denote which basis it is, and then which vector. So this right one denotes which basis, and this left one denotes which vector. And so we'd get 1, a2 times w1 plus 1, 2, a22, w2 plus let's say am2 wm, right? And so, well, what if we take each of these every a, right? So this a is going to be for your first basis, and then this a is going to be for your second basis. So what if we write these all as column vectors? Okay. So this is one column vector. And then our second column vector is going to be a12, a22, and then all the way down to am2. So we're going to just write the coordinate representation for this vector and this linear transformation in terms of this basis. Okay, and so what if we just merge these together? What if I were to remove these brackets and make them the same matrix? Well, then in that case, that's what we're going to call the matrix representation. So if you use the n tuples that show your representation of the matrix, of the linear transformation applied to your first basis, and how that's a combination of the basis for your second vector space, a linear combination of that, well then you can merge those as columns of your matrix, and then that becomes a linear transformation of T. Okay, so I will demonstrate this with an example because that probably made no sense. So T A B, that's going to equal 2at squared plus a plus b t plus 3b. And so let's just take a standard basis for, we're taking R2 here and we're mapping it to, we're transforming it into P2 here. So let's just say we have the standard basis for both, just to make it easy for us. So we're going to say that T of 1, 0, that's going to equal, since we're given our transformation, that's going to equal 2 of t squared plus 1 of t plus 0 of 1. And that's going to just, if we make our coordinate representation, that's just going to be 2, 1, 0 with respect to, let's call the standard basis for P2, let's call it C. And then, yeah, let's call it C. So this is going to be with respect to C. And so if we do the same thing here for 0, 1, that's going to equal 0t squared plus 1t plus 3, 1. And so that's going to give us 0, 1, 3 with respect to C. Okay? So we're just representing the operation done to this based on our basis here. And so we get these two vectors. And so then we can say that, say, A, which is going to be our matrix representation of this linear transformation, and we're going to denote it with superscript C to show that it's dependent on this basis. And so this is just going to be equal to these two smushed together. Okay. And so normally you could also write B down here. So if this was a basis that is non-standard, so if the basis for R2 wasn't standard, then we could say, well, we need to write B down here. But since it's standard, you can just forget about it. But because we're modifying to a different basis here, we always need to include this C here. Okay? So if we were changing from R2 to R2, then you wouldn't need the C either. But since we are, you need to include the C, but the B is optional because it's standard basis. Okay, and if you were to do this with, let's say, standard basis equals 1, 1 transposed, and then 1 minus 1 transposed. So why don't you go ahead and try this? So what you do is you're going to plug this into your transformation, plug this into your transformation, and then get your output, and then put them together in your matrix. Okay, so go ahead and try that, and then I'll come back, and then we'll do it together. Okay, so hopefully you've had a chance to do that. And I apologize if the video is getting a bit long, but I think there's a lot to cover in this, and looks like we'll make it a two-part. So for this example, T11, I'm gonna plug that into our transformation. So our transformation, that's gonna give us 2t squared plus 2t plus 3 times 1. And what's that? That's going to be 2, 2, 3. With respect, this should not be an equal sign. Apologies. With respect to C. And then if we do the same thing for the other vector, that's just going to be equal to 2t squared plus 0t minus 3 times 1. And so that is going to give us 2, 0, minus 3, C. And so now what we can do is we can smush them together. So put the first one first, first column, and then the second column. Put them together. This is with respect to C. So since it's our second basis, we put that up top. And then our first basis, which was B, since it's not non-standard, we need to denote it. We need to make sure we write it here. And then we need to do the same thing for our A, which is just going to be our matrix. Okay. And so that concludes this video, and we'll continue on with a couple more examples and some more matrix representations in the next video, but I'll see you then.